Hello, AP Statistics. I'm going to go through this activity that the 6.5 confidence interval for P practice free response question. You should have at this point already attempted this problem for 15 minutes on your own. And then the rubric is on the back, but I think it'd be easier if you also had an exemplar response as well. So that's what I'm going to be doing here for you now. So taking a look at this, a certain company makes 3 grades, A, B, and C, of a particular electrical component. Historically, grade A components have a 2% defective rate. I'm just going to underline that because it feels like it might be important later. Grade B have a 5% defective rate, and grade C have a 10% defective rate. Since grade A components are less likely to be defective, the company can charge more money for those components than it can charge for the B or C, grade B or C components. Similarly, the company can charge more money for grade B than it can charge for grade C. That's all just information for us. Recently, the company found a batch of components in a warehouse that were known to be of the same grade, but the grade was not labeled on the components. To determine the grade, A, B, or C, the company selected from that batch a random sample of 200 components, which contained 16 defective components. Construct and interpret a 95% confidence interval for the proportion of defective components in the batch. So when we're asked to do this 95% confidence interval, immediately we should think, oh, I need to do my state, plan, do, conclude. So we're going to go through that now. To state, we want to state the parameter we are estimating and the confidence level, and we want to make sure we are being specific here. So as we're looking, as we are looking at this activity, to state the parameter, we are looking for the proportion P, which is the true proportion oh, I see it right here, the proportion of defective components in the batch. So the true proportion of defective components in the batch. And then I also want to put my confidence level. So my confidence level is 95%. It doesn't say it here, but this would also be a place where we could put our sample proportion. And our sample proportion, we see we had 16 out of 200. So my P hat is 16 out of 200, which if I do that calculation, I need to grab myself a calculator, which I will need later anyways. 16 divided by 200 is a proportion of 0.08. So then planning, so that's my state, excuse me, that's state. So it's the true, I'm looking for and interested in the true proportion of defective components in the batch. I have a confidence level of 95%, and my sample proportion was 16 out of 200, which is 0.08. So my plan, I have to identify the appropriate inference method and check my conditions. So my appropriate inference methods here are first, we're going to perform a 1 sample Z interval for P. A 1 sample Z interval for P. Notice that is not for P hat. That is for P. And then I need to check my conditions for inference. The first thing we need to check is random. And we see here that we have a random sample of 200 components. So that is, in fact, so the 200 components were randomly sampled. So that checks. Then I need to check, we don't need to check for independence here, but we do need to check for my sample size. And because this is a proportion, we want to take a look at our large counts condition, right? Because as long as we fit that large counts condition, then we can use the normal distribution and those types of calculations to, we can use the calculations that we need in order to be able to construct our interval. So my large counts condition, since I don't know what the true proportion is, I'm going to use the p hat. So that's n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. So 200 times 0.08 was 16. That is greater than or equal to 10. And 200 times 0.92, which is 1 minus 0.08, is 184, which is also greater than or equal to 10. So that also checks. Next, if the conditions are met, perform the calculations. So my conditions are met here, so I can now perform my calculations. So I'm going to go to my reference page for my calculations. So remember that our confidence interval is the statistic plus or minus the critical value times the standard error of the statistic. That's our margin of error, and we can find everything we need on the back. So my formula is going to be my point estimate, which is my statistic, plus or minus the margin of error. That's my general formula. My specific formula then for this one is going to be p hat plus or minus z star times my standard error of the sample statistic on the back of this page. We've got that standard error of the sample statistic here. So times the square root p hat times 1 minus p hat over n. And then I need to fill in this formula. So I know that my p hat was 0.08. So I have 0.08 plus or minus my z star for a 95% confidence interval. Ooh, excuse me. Was 1.960. Remember, if you forget, you can use your inverse norm. Was not right. Just the tail percentage, that's why, excuse me. So if it's 95%, then I have let's see, 95, sorry, my brain is not working today. 95, 100 minus 95 divided by 2. So I have 2.5. Inverse norm. $2.5. Lovely. I will take a look at that and figure that out again. I apologize. We'll figure that out. It's probably supposed to be 0.025. Anyways, just to continue this, times the square root of 0.08 times 1 minus 0.08 divided by my n of 200. Then I'll use my calculator to calculate that margin of error. So 1.960 times the square root, 0.08, times 1 minus 0.08, divided by 200. So that's going to be then 0.08 plus or minus 0.038. I just put that margin of error part into my calculator, and then I'm going to actually do this calculation. So I'm going to do the subtraction first, 0.08 minus 0.038, which is going to be 0.042, 0.08 plus 0.038, which is 0.118. And then as our conclusion here, we need to interpret the interval in the context of the problem. So in terms of that, we would say we are 95% confident that the interval from 0.042 to 0.118 captures the true proportion of defective components in the batch. All right, part A is complete. Part B then asks, does the interval calculated in part A allow the company to clearly determine the grade of component that was produced in the batch? Explain. So if we go back to the top, back to this, what we have up here, this is coming from that original information. So the true proportion of defective for A was 2% or 0.02. The true proportion of defective for B, which was 5% or 0.05, and the true proportion of defective for C was 10% or 0.10. So what I'm thinking about here as I look at the confidence interval that I calculated, I have 0.042 to 0.118. So looking at that, it is very unlikely that the batch contains grade A, because that is outside, that is not, 0.02 is not captured in my confidence interval. However, we cannot determine between B and C because both of those values are captured by the confidence interval. So what we would want to say here is something like, while we can be confident the batch is not grade A, because the true proportion of defective grade A components, which was 0.02, is not captured in the confidence interval. We cannot determine between grades B and C, since both of their true proportions are captured in the interval. If I zoom out here, you should be able to see pretty much that full answer to both parts A and B here. Just to note, for right now, I've given you the state plan do conclude. On the actual AP exam, and as we move throughout this unit, that you will not see those pieces. We need to just know that those need to happen, and you can label them in your work as well. That state plan do conclude. It's a great way to organize your work, but that will not be there for you.